a cubed, right? And a cubed is, where is it? Here, right? That is not e. A cubed is different from e, right? These are all distinct, all 10 of them are different. So a cubed is not e. So a cubed is not e. So therefore we have shown that AB, the order of AB, is not 2. It's not 2. Because the result here, a cubed, is not e. Therefore the order of AB is not 2. Alright. Okay, so let's try AB cubed. Well, that's AB squared. AB is BA squared, just so plug that in, BA squared here. AB squared, wait a minute, BA squared, yeah, here. And AB squared from here is A cubed. So this becomes BA squared from here. AB squared is this, so plug that in. And you've got A squared A cubed, that's A to the 5th. But the order of A is 5, so A to the 5th is E. Okay, so you've got BE, which is B, right? Okay, now let's try AB to the 4th power. So this is the same as AB squared. And AB squared we showed is A cubed. AB squared is A cubed. So you get A cubed, that's A to the 6th, that's A, right? Because A to the 5th is E. So that's A, right? Now let's try AB to the 5th power. Well, that's AB cubed times AB squared. AB cubed is B. So just for here, just put B. And AB squared is A cubed. Okay, so BA cubed. Now BA cubed is here. This is not E. Remember, all these 10 are distinct, they're different. So BA cubed is not E. So BA cubed is not E. So the AB to the 5th power is not equal to E. But AB to the 2nd power, squared, is also not equal to E. Ooh. So that means AB is not of order 2 and it's not of order 5. Therefore, but it must be because the order of the group is 10. Right? So we've got a contradiction. So the possibility that this equals this doesn't work. Contradiction. So kill case 2. So case 1 worked, case 2 did not work. Alright, so now let's try the third possibility. So we have that one, first possibility, second, third. This is our third. AB equals BA cubed. So let's try this one. Okay, so again we just take powers of AB, AB squared, AB cubed, A to the B to the 4th, AB to the 5th. So AB squared is just this. AB is BA cubed, so plug this in here. So you'll get AB squared, A to the 4th. B squared is E. Okay, so you're just left with A to the 4th. Right, AB cubed, that's AB squared AB. AB squared we just found was A to the 4. AB. So you get A to the 4th A, that's A to the 5th, that's E, because the order of A is 5. Right? So just B. Now the order of AB here is A to the 4th, it's not E. Therefore the order of AB here is not 2. Right? Because if the order were 2, this should be E, but it's not. It's A to the 4th here is different from E. Alright, so let's do the 4th power, AB to the 4th, that's AB squared. But what is AB squared? It's A to the 4th. So squared, so you get A to the 8th. And A to the 5th is E. So you're left with A cubed, right? Now AB to the 5th is AB cubed, AB squared. AB cubed is just B, so put a B here. And AB squared is A to the 4th. So you get BA to the 4th. That's this. Now, These are all different, so BA to the fourth is not equal to E. Right? So this is not equal to E. So AB cannot have an order 5. Right? But it also cannot have an order 2, because this is different from E. And this is also different from E. Therefore, we've got another contradiction. Right? It's the same as case 2. Alright, so that's out. That possibility eliminated. Contradiction. Alright, case 4. What was the fourth case? This one. So AB might equal BA to the fourth. Alright, let's try that. Now, we know A to the fifth is E. That's assumed here. We know B squared is E. We've derived that here. And we're trying to find what AB is. Now, if I multiply on the left by A, now AB is BA to the fourth, right, here. And I multiply it on the right by A. So I'll get BA to the fourth A. So A to the fourth A is A to the fifth, that's E. So BE, and that's just B. Now, so you've got ABA is B, alright? Ring a bell? ABA equals B. You've seen that quite a few times. So the presentation for the group for case 4 is you've got A to the fifth is E, B squared is E, and ABA equals B. And two generators, A and B. You know, obviously, A and B are the generators because they generate the whole group, right? Just those two elements, A and B. So remember, that's the definition of a presentation: the set of generators and a set of relations, like A to the fifth is E, B squared is E, and ABA is B. So there's those three relations, and that is the presentation, if you remember, of a dihedral group. And N now is 5, right? So G now is isomorphic to the dihedral group 5. So the symmetry, in other words, the symmetry operations of a pentagon, right? A regular pentagon, where the 5 sides are all of equal length. Okay? All right. Well, summarizing, for a group of order 10. We now have three different, non-isomorphic types of group. There's the cyclic group, order 10. Yeah, that's always the case. We have this direct product type here. Where is? Where was that? Oh, here. Yeah. C2, C5. Okay. And we've just derived that the dihedral group, G10, is isomorphic to the dihedral group as well. It's a third possibility. So the answer then for how many different non-isomorphic types of group can you have for G10? The answer is 1, 2, 3. Okay, so for G9, it was only two different types, the cyclic group and this direct product. Okay, now you probably got a feeling, if you went up higher and higher orders of groups, the analysis gets tougher and tougher, and that's probably the major reason why mathematicians have not tried to classify all possible groups. That would be just monstrous. So it's an open, as far as I know, an open question. It's still, it's not been done. Only for certain specialized types of groups do you have classification theorems. Trying to classify every type of finite group, that would be monstrous. Yeah, I'll leave that there. I still plead somewhat. That's an area I need to look into a bit further. All right, so that's the end of the problem-solving session. Next lecture, lecture 16, will be, I think, a lot simpler. This analysis here gets pretty heavy and very dense, dense, logical, step-by-step reasoning. Next lecture, fairly easy. It's on the concept of something called equivalent relations. Is that right? Hold on, let me check. So, yeah, equivalence relations. And why? why talking about that? It's basically just a stepping stone. We need that knowledge. We need to know what an equivalence relation is in order to do the following lecture. So two lectures from this one. That would be lecture 17, and that's on the notion of quotient groups or factor groups. Same thing. There's two different labels for the same concept. And the idea of a quotient group is one of the highlights of this whole course. It's basically the idea that, in a sense, in a manner of speaking, you can actually divide a group. You can take a group of a certain order, and out of it you can, under certain circumstances, you can extract a smaller group from that bigger group. And that group is called a quotient group, the result of a division, or a factor group, sort of related. Okay, so now that's a beautiful piece of math. I think by the end of lecture 17, this is lecture 15, you will be really quite impressed by what finite groups can do. So the very notion, the concept of a quotient group is one of the highlights, as I was saying, of finite group theory. It's one of the big results. And to be able to understand that, we have to do a fairly short, fairly easy chapter, but we need the knowledge, and that notion that we need, the stepping stone, is equivalence relations. So that'll be the next topic for the next lecture. So until then, ciao.